Welcome everyone for this edition of the BRAG, Brazilian Algebraic Geometry Seminar. This is in fact a young BRAG, and today's speaker is João Paulo Lindquist Figueredo from Impa, and he will speak on regular foliations on rationally connected threefolds with NIF anticanonical bundle. Please, João Paulo.
Thank you, Carolina. Thank you everyone for being here listening. And thank you for the organizers for the invitation. So I'll talk about part of my thesis work that I'm finishing, which I'm finishing now in the following months. And this is a problem on determining when foliations have algebraic leaves. So I will start with a summary of the program of my talk. I'll start with an introduction. Then I will talk about foliations and the foliated MMP, where MMP stands for Minimal Model Program. And then I will talk about regular foliations on rationally connected manifolds and regular foliated MMP. The NEF reduction map, and I will finish with the main result that I want to show you. So I start with an introduction on the main theme of this talk. So in this talk, we will study the problem of showing when a regular foliation has algebraic leaves. So what is a foliation? A foliation, we can start defining by the classical definition starts with a regular foliation. Then we can extend to singular foliations. So regular foliation on a manifold is a way of decomposing the manifold into a disjoint union of leaves, which are some manifolds. Oh, what does that mean? More precisely, we decompose X into a disjoint union of submanifolds, immersed submanifolds, F alpha. They all have the same dimension R, and this R will be the rank of the foliation. I will also use the term codimension of the foliation, which is the dimension of X minus R. So these are just the rank is just the dimension of the leaves, and the codimension is just the codimension of the leaves. So what else do I ask? I ask that locally the foliation is given by an immersion. So what is that? Locally around each point of X, I can find a neighborhood, open neighborhood, U, which I can decompose as a product of dr times dn minus r, where d is the unitary disk in C. With these two projections in the foliation, the leaves of the foliation inside U or restricted to U are the fibers of P2. So a drawing to illustrate this. This is U, and the F alphas are the leaves restricted to U. So the foliation here is given by this immersion, subimmersion. So one example, I can take X, the Cn, a fine space, and delta, a vector field without zeros. So through each point of Cn, I can find a curve which is tangent to the, I can find one and only one curve which is tangent to this vector field. And locally, these curves, the solutions of this ODE are given by a subimmersion. So this is a classical, the prototype of a foliation. So this is a rank 1 foliation too. The main problem I want to track is how to determine when the leaves of a regular foliation are algebraic submanifold of X. And what I try to present here is a very specific. I will motivate why this result is important, but I just want to say this is our main goal, to motivate this and to give you an idea how to prove this. So let X be a rationally connected smooth threefold such that minus kx is an f. If f is a regular foliation of codimension 1 on X, then the leaves of f are algebraic, and moreover, they are rational surfaces. They are projective, smooth, rational surfaces. So let's start with a formal definition of foliations, not only regular foliations, and I'll try to give them more general, the most general definition. So let X be a normal variety over the complex numbers. It doesn't have to be complex numbers, but I will just uh, study this case. A foliation f on X is a coherent subshift of the tangent bundle of X, such that for every two vectors, every local sections, two local sections, you can think of this VW as two vectors because F is a subshift of Tx. So you can take the lip bracket of two vector fields on U. And I just ask that these two, the lip brackets of the lip bracket of n2 vectors on F are still on F. In the second, in the second, wait, in the second condition is that the quotient is torsion free. So why do I make this definition? What's the relation of this definition with the regular foliations definition I gave in the introduction? So a theorem a classical theorem on the theory of manifold. If I start with a manifold and take a subvector bundle of the tangent bundle, such that any two vectors of this vector bundle, subvector bundle, the lip bracket is still a vector on this vector bundle, then I can find a foliation on X such that the tangent bundle, the tangent, this vector bundle is exactly the vector bundle given by the vectors which are tangent to the leaves of the foliation. So this is the first condition on this definition. So with this, we can see that on X0, there is a foliation, a regular foliation, such that the tangent vectors to this foliation are given by F restricted to X0. So this is only to make a more algebraic definition. And the second condition says that we can take this x0 to have the complementary of x0 to have codimension at least 2. That's the reason we make this. So this is the consequence I just gave you. So how are we going to treat the problem of foliations is to make an analogy with the theory of birational geometry class, which is very very much studied these days. So in birational geometry, to each variety, we can associate its canonical bundle. And this canonical bundle tells a lot of information, geometrical information on the variety. For instance, if the variety has negative canonical bundle, then the variety is Fano, and for example, if it is Fano, then uh, it's rationally connected. For example, one example I can give. So for foliations, we make a very analogous definition. So a foliation is defined by a subvector, a subsheaf of the tangent sheaf, and I can take the determinant of this sheaf and take the dual. So this will be a divisorial sheaf. In other words, it's given by a sheaf of this way, OX of a divisor. So this will be a divisorial sheaf because it is, oh, I forgot the word, but it's a divisorial sheaf. So the the main the main reason we define this is because we will see that the positivity or negativity of the canonical bundle, the canonical class of a foliation tells a lot of information of the foliation itself. For instance, we have the following theorem by Miyaoka. If S is a smooth surface and F a foliation of rank 1 on S, if KF is not a pseudo-effective divisor, in other words, if it's not in the closure of the cone generated by the effective divisors, then the foliation is given by a rational fibration. Or in other words, the leaves of the foliation are rational curves. And in particular, the leaves are algebraic. So this is one example of the main problem we are trying to study, showing when a foliation has algebraic leaves. So this is one instance where this happens. So to make precise the concept, we say a leaf of a leaf of a foliation F is algebraic if uh, the dimension of L as a manifold is the same dimension of closure, the Zariski closure of L in X. Or in other words, or it's the same as saying that L is a Zariski open subset of the Zariski closure of L. So how are we going to study the problem of determining when a foliation is algebraic in higher dimensions? So this here is for foliations on surfaces. For higher dimensions, we can use a very recent results on the theory of birational geometrical foliations, which is the minimum model programs for foliations. So what is that? Let me introduce this concept. So the minimum model program is first appeared in the context of varieties. So what is that? It tells conjecturally that uh, i- if dimension of x is at most 3 is not a conjecture theorem, but it tells that If X is a projective variety with good singularities, we can run a sequence of elementary birational maps uh, such that in the end result, Xn has either a Nef canonical bundle or it is a Moore fiber space, or in other words, a vibration Xn to Y whose fibers are Kxn negative, or Fano. The fibers are Fano varieties. So this tells that uh, to classify birationally the varieties, we can restrict our study to varieties with Neff canonical bundle or to Fano varieties. So we can make a very analogous statement for foliations. We start with a projective variety with good singularities. I'm not saying what good singularities are, but this is another subject you study. I don't have time to introduce this. So you start with a projective variety with good singularities and a foliation with also good singularities, which are analogous to the good singularities for varieties. Then I can find a sequence of elementary birational maps such that either the canonical, so in each step of this sequence, I obtain a new foliation on each xi. So I can define a foliation on an open subset of xi and extend it to the whole xi. So it's easy to see that each each time uh, each time I can induce a foliation from the previous step. So I end up with xn and fn foliation of the same rank of the original foliation on X. And the conjecture is that, in analogy to the classical MMP, is that either KFN is NF or there is a fibration Xn to Y whose fibers are KFN negative. Turns out that this is true if dimension of X is at most 3. So for dimension 2, this is by Brunella, Maquila. In dimension 3, which is more recent, Cassini, Spicer's Fault. So in this talk I use this result for dimension 3. So to motivate the main results I presented in the introduction, which I remind you is that I want to show the regular foliations on rationally connected manifolds are algebraic, satisfying some conditions. So to motivate this, I start showing that this is true. Uh, the analogous result is true for foliations on surfaces. So how to say this? So start with a SFN Heisenberg surface. So this is a P1 bundle over P1. So the map, the fibration, rational fibration, defining S as a P1 bundle over P1 defines a regular foliation S. So every fibration defines a foliation. You take the leaves as being the fibers of the fibration. And this is a regular foliation, and the leaves are rational. Is that the reciprocal of this is true as well. More generally, if you get any regular foliation on a rational surface, uh, this foliation will be algebraically integrable with rational leaves. So this is a very striking result on classification foliations. It tells that there are very few regular foliations on rational surfaces. And they don't have they are very rigid. They don't have a lot of dynamics. So I want to show this. So the conjecture, I want to generalize this to uh, higher dimensions than 2. So I take the conjecture made by Frederic Touzet is that if X is a rationally connected manifold, so rationally connected is the generalization uh, of rational. We could take rational as the generalization of rational surface. But if we take only rational, we would miss examples like conic bundles over rational surfaces. They may not be rational, but they are rationally connected. So the conjecture says if X is a rationally connected manifold and F a regular foliation X, then F is algebraically integrable and the leaves are rationally connected. And one progress in this conjecture was made recently by Druel. He showed that on Fano manifolds, the conjecture is true. So I remind you that Fano manifolds are rationally connected. This is a result by Kolar, Miyaoka Mori, and independently Campana. So he showed that regular foliations are algebraically integrable, and the leaves are Fano submanifolds of X. In this talk, I want to study the conjecture, to this conjecture, for foliations on threefolds. And I didn't write here, but I also only consider foliations of codimension 1 here. So in our context, it we start with X smooth and F regular, and using the foliated MMP, we can get a model such that the final result has NF canonical or is a modifier space. But in this case, when both X and F are smooth, this process is very much simplified. What I want to say is that on each step of the foliated MMP, when we start with X smooth and F regular, on each step we preserve regularity of both X and F. In other words, every Xi is smooth and Fi is regular. So how, and moreover, I want to show. So let me make a small remark about how to obtain the steps of the foliated MMP. So this star here will be the foliated MMP of our original threefolds in regular foliation. So how to obtain the steps of this MMP? If you know something about the classical MMP, you know that you have to start contracting the negative extremal rays on the cone of curves, of effective curves on X. And there is a cone theorem which gives a characterization of this cone. And for foliations, this is true as well. So these extreme arrays are generated by rational curves, and these rational curves are moreover tangent to the foliation. In other words, they are contained in leaves of the foliation. Now, for foliations, we can define a partial connection on the normal bundle of this foliation, an F connection. So this is a partial connection because I only derivate vectors along vectors tangent to the foliation. So this is called Bot's connection. But the implication this has is that if I get a tangent variety, in this case a curve, to F, then the restriction of the normal bundle to C, this connection will turn out to be a holomorphic connection on this normal bundle restrict to C. So a bundle with a holomorphic connection has zero Chern classes. So C1 of NFC here is zero. In particular, C1 of DXC is equal to C1 FC. In other words, KFC is equal KXC. So the contractions of KF negative curves are contractions of KX negative curves as well. And in particular, the steps of the MMP, which are contractions of KF negative curves, are steps of the classical MMP for KX, for the variety. So if star is a regular foliated MMP, then the steps of stars are contractions for the classical MMP for X. And they only contract curves which are tangent to the foliations Fi. So we run the MMP for foliations. We end up with Xn and Fn smooth. We only contract curves, only contract things which are tangent to the foliations. And the final, if you have a more fiber space, the fibers of the more fiber space are tangent to the foliation as well. So we have these two cases again. KF is NF, or there is a more fiber space in the classical sense, because we saw the contractions for the foliation are contractions for the variety. Y is smooth by the classification of more fiber spaces of dimension 3. The fibers are KF negative and tangent to the foliation. In this case, we have two possibilities. Either dimension of X is 2 or dimension of X is 1. Dimension of X of Y is 1. In this case, we have a Diopiezo fibration. And if dimension of Y is 2, this is a conic bundle. Moreover, the fibers of F are to the foliation. So we see in case 1, this is a fibration by surfaces which are tangent to the foliation. So this fibration gives the foliation. And in case 2, we induce a foliation on Y whose pullback is F. So in case 1, F is induced by F, and in case 2, F is the pullback of foliation Y. And this foliation is regular as well. We can show this by a calculation, a local calculation on local coordinates. So on surfaces, we know the conjecture, Touzet's conjecture is true, so G is algebraically integrable with rational leaves. This implies then that F is algebraically integrable with rational leaves. So the corollary of this is that if we end up with a more fiber space, in other words, if the canonical is not pseudo-effective, then the original foliation F is algebraically integrable with rational leaves. We just need to treat now the other case to prove the conjecture. So the other case is when we end up with a foliation with Neff canonical bundle. And I wasn't able to show this in general. I was only able to show this when the anticanonical bundle of X is Neff, because in this case I have a map to which helps me to arrive at a contradiction. So in this case, uh, I want to show that in all cases, the canonical bundle of the foliation is not pseudo-effective. So I want to show that the other case is impossible. So I want to show some kind of contradiction. In this case, I'm able, with the aid of the Neff reduction map of the anticanonical bundle, when the anticanonical bundle is Neff. So what is the anticanonical bundle? The Neff reduction of the anticanonical bundle. So for threefolds, this will be a holomorphic map to a normal projective variety, which is obtained by the we take the equivalence relation. So we quotient out the curves which are numerically zero, such that the anticanonical bundle is numerically zero, on which the anticanonical bundle is numerically zero. So what are the conditions? The anticanonical bundle is numerically trivial on the fibers of F, and for the general curve, which is not contracted by F, the anticanonical bundle has positive intersection. There, in other words, is not numerically zero. So in our case of X rationally connected, and I will show this happens too, we can characterize this Neff reduction. So if this other condition, technical condition, if X is a conic bundle or admits a divisor contraction, then the canonical, the Neff reduction is a K3 fibration. And the anticanonical bundle is the pullback of O1. So this allows us to show our main result. I only present a sketch of the proof. If X is a rationally connected smooth threefold with minus Kx Neff, if F is a regular foliation of codimension 1 on X, then F is algebraically integrable with rational leaves. So the idea is run the foliated MMP. We saw that this ends up with Xn smooth and Fn regular. If Xn Fn is a more fiber space, in other words, if Kf is not pseudo-effective, we showed this is the result is true. The foliation is algebraically integrable with rational leaves. So let's suppose this is not true, that Kfn is Neff. Since Kx minus Kx is Neff, the square is positive. Moreover, since Fn is regular by the Bot's vanishing theorem, the square of the normal bundle is 0. So I have here nfn equal to kfn minus kxn. The square of the left hand side is 0. And here the square of this is greater than equal to 0, the square of this is greater than equal to 0, and this is nef, and this is pseudo-effective. So I can use a Hodge theory to show that this implies that these two divisors are dependent. One is a multiple of the other. And I can show that in our case, this is the case. KFN is lambda KXN for lambda negative. In particular, minus KXN is nef as well, and the square is 0. So using the result I presented by Bauer Preternel on the characterization of nef reduction, in our case, I have to make some other remarks here, but I don't have time. So in the end, we show that F is a K3 fibration, the nef reduction. Now, if I take a one form defining, a global one form defining, twisted one form defining Fn, and take F, a general fiber of the nef reduction, which is a K3 surface, if I restrict omega to F, this will be an element of H0F omega 1F. And this is 0 because F is K3. So F is tangent to Fn, and Fn is the induced by the nef reduction. In particular, this shows that Fn is algebraic, but we can show that this is impossible because so this is the one thing I will not do here, but we show that this cannot happen. So for this, we use the classification of the steps of the MMP by Mori and use the characterization of the nef reduction, and we can arrive at a contradiction. So KFN cannot be nef. In other words, it has to be, we end up with a Moro fiber space and we finish the result. So just giving the bibliography, if you want to see. I use a lot of results by Brunella, and these very recent results by Cassini Spicer, Cassini Spicer 2. Here, Spicer. This is the only one that is published. The other ones are only on archive. So this is it. I finished my talk.
So are there questions for João Paulo? Let me ask you something. So you, when you put the conjecture about the foliated MMP,
Yes.
Yes, this one. So you explained that okay, this is proved in dimension 3. But let me ask you something. In the case of regular foliation, suppose that in arbitrary dimensions, suppose that the foliated MMP exists. So it's true that automatically every for a regular foliation, is it automatic that a F MMP is going to be a regular classical MMP?
Yes. It depends if we only contract curves which are tangent to the foliation. Because if we do that, then the same thing here happens. So the steps of, we only need this to happen. Steps of the KFMMP are steps of the KXMMP.
And so to prove this in the three-dimensional case did not follow automatically from the existence of the steps, or was.
No, you need to show the you need to show the con theorem for foliations.
But the
So
okay.
Yeah, this is a consequence of the cone theorem, if I understand things right.
yeah, this here.
And it's known only for foliations of dimension 1 in arbitrary dimension and foliations of dimension 2 in dimension 3.
Yeah, but for foliations of rank 1 on arbitrary dimension, I don't know if this is written.
It's written, the semi-stable reduction of foliations by McQuillan.
Okay, but this is not published, is it?
No, but...
Okay.
But it's written.
Okay.
I think that there is someone raising your hand. Please, I do not know who this person is, but go ahead and unmute and ask if you want. Okay, maybe it was an accident. So are there more questions for João Paulo? So if not, let's thank him again for this talk.